So this is the buck converter. You are familiar with the circuit by now. We need to rate the components, the switch, the diode, the inductance and the capacitance. These are the four elements that we need to design. To design this, to rate the components properly, we need to have an understanding of the various waveforms that are pretty critical. Now the pole voltage Vp is a very important waveform that you should understand, because it will help in rating both voltage rating of both this diode and the transistor. The current waveform of the inductor is very critical, because this is an important part in this component in this particular topology. See that this current through the inductor gives information about the current flowing in the input, and therefore the current flowing in the transistor, the current flowing in the diode, because the freewheeling current also flows through the inductor. The current flowing through the inductor also divides into the capacitor current and the current through the load. As we had discussed earlier, the current through the capacitor will have a zero average value in steady state, and the current through the output load will be a pure DC. So keeping these things in mind, let us construct the waveforms, and based on the waveforms we can just read off the rating values of the various components. Let us now start by placing the x and y axis. Now I have here three x-axis, which is the time axis, and on the y-axis we have three important things. Vg is nothing but the gate signal which we will be applying at this point. I didn't want to put it as Vb because it may be confused with battery voltage, so therefore I am calling this one as Vg, as we had indicated in the simulation, and this is the signal to drive this on or off. So what is that signal? And before that, the other important variable voltage that we need to see is the pole voltage. Pole voltage, the voltage at this point with respect to the ground, and then the current, that is the inductor current. Now the pole voltage will give information on this diode rating in terms of voltage, and the rating of the transistor, and also the voltage across the inductor to check for the volt second balance. The current of the inductor will give a lot of information on the input current, the current through the diode, current through the capacitor, current through the load. So let us look at them one by one. For the voltage, let me install this here. So this is the waveform, the voltage waveform that we would see at the base or the gate of this power semiconductor switch. The time when the pulse is high, then the switch is on. The time when the pulse is low, the switch is off, and during that time the diode is freewheeling. So this time would be the dTs time, and this time would be the 1 minus dTs time. This is the on time and this is the off time. So we shall mark them accordingly. So let me place the marks here. So this is the dTs time and this is the 1 minus dTs time. Now such a waveform we will apply at the gate of this. So what happens? So during the time when this is on, V in comes to the pole, so the pole voltage will be V in value, and during the time when this is off, the diode is freewheeling in this path and the pole voltage is connected to the ground, so it will be 0. So let us mark that. So I am going to place this waveform here. So see here that the blue colored waveform is the pole voltage waveform that appears here. During the time when the Q is on, the pole voltage is high and it is V in value, and the value there, let me indicate by the symbol V in. Now this has an average value, so let me indicate the average value by a line like this. So this is the DC value that you would see at the output, because this is the average of this. What is the average of this? V in this area, and this portion will get averaged out. This will fill up here, and then you will get a smooth DC, and that is our V0. V0, which is V in into D. V in into D is the average of the blue waveform. Now, if I take the average as V0, this amplitude I am indicating by the arrow will be V in minus V0, and this amplitude from the average value to 0 would be V0. So this portion in fact would be the waveform that you would be seeing across the inductor. So you see that the portion above the average and the one below the average. So that yellow portion is the one which will be appearing across the inductor, and there should be volt-second balance between the top portion of the yellow and the bottom portion of the yellow portion of the waveform, above and below the average value. So the yellow portion of the waveform is what is called the VL, or the voltage across the inductor. So this way, the voltage, the pole voltage here has so much information in it. It gives you the what is the average of the output. It gives you the voltage across the inductor and the volt-second balance that is happening. And with this, we can rate these two components. Now let us see. During this period, that is during the DTS period, the transistor is on. When the transistor is on, the pole voltage here is V in. Then what should be the peak inverse voltage of the diode? The peak inverse voltage of the diode should be V in, or at least greater than V in, because this diode has to withstand a value, the potential equivalent to V. Now when, let us say this is off and this is freewheeling. So when this is freewheeling, this is pulled to the ground. So the emitter is pulled to the ground and this is at V in. So the voltage withstanding capability of this BJT or any other power semiconductor switch which is placed here should be V in, which is this value. So you see that just by looking at the waveform, the pole voltage waveform, we have found two important ratings of these two devices: the voltage withstanding rating of the switch and the voltage withstanding rating of the peak inverse voltage of the diode. Now let us look at the inductor current. I have drawn a green line here. The green line here is not the inductor current, but it is the current that is flowing through the load. Assuming very negligible ripple across the output, I have approximated it by a straight line, and this is the current, that is DC current, flowing through the load. We will call that one as I0. So this is I0. And now how will be the current through the inductor? When the transistor Q is on, the voltage here is V in and the voltage here is V0. So in the steady state, V in minus V0 is applied across the inductor. So let me take the writing pad to give a view of what is happening. So consider this inductor, and it is seeing the voltage across this VL, which is equal to V in minus V at some time, let's see. So we know that VL, which is equal to L di by dt, and di by dt, where I is the current flowing through the inductor, is given by VL by L ratio, or it is Vn minus V naught by L ratio. So this is the di by dt, or the slope of the current waveform. So at this slope, the current waveform should increase. So if I draw the slope during the time when the voltage across the inductor is V in minus V naught, it should increase like this, because V in is a constant, V naught is a constant, L is a known constant. So the rate has to be a linear one, and this is V in minus V naught by L. And during the time when the switch is off, we saw earlier that this side of the inductor becomes 0, and here it is still V naught, and what is applied is minus V naught. So what is the rate? Di under such conditions, di by dt would be a change in color, still VL by L, but now it will become minus V naught by L. Now minus V naught by L indicates negative slope, so it should start falling at this rate. So this would be minus V naught by L, a negative slope, falling rate. And then the subsequent cycle again should go in this fashion and start falling. So this will be the shape of the current through the inductor. Now what will be the average value? The average value flows through the output, and that is nothing but I naught. And the ripple value, the one with that component with zero average, will flow through the capacitor. So through the capacitor, the one marked like this is what is going to flow. So this is what we can expect, and let us go back and have a look at the circuit. So the average value of the inductor current is I naught, and that is what will go through I. The ripple component of the inductance will go through the capacitance, and there will be a ripple component here. So let us place the ripple component here and see what. After placing the ripple component here, you see that the wave shape is like this, just like as we had discussed. During the time when Q is on, inductor is charging up, and this charging up at rate is V in minus V naught by L, and then the inductor is discharging during the time when it is off. It is discharging, it is freewheeling like this, and it is falling down at the rate of minus V naught by L, and it keeps on repeating under steady state condition like a triangle. And the one that is filled up here, the colored filled up portion, is the zero average portion, and that is what will flow through the capacitance. The filled up portion is the capacitance current. The average value of that is the current flowing through R naught, and this entire wave shape is the inductor current. So you see that you get again here a lot of information in rating the components. If you look at the current flowing through the BJT, the current flows only during this portion, something like this. So let me see. So only during this portion the current through the BJT flows. So you can rate your BJT for this. It has a peak current of I naught plus this ripple peak. So if I say that the ripple amplitude is like this, delta IL, then the rating of the current for BJT will be I naught plus delta IL by 2, which will be this peak. That will be the peak current. The average current rating will be I naught into duty cycle D. And for the diode, it will appear like this. During this time, the diode, whenever the switch is off, the diode is freewheeling, and during this time there will be current flowing through the diode, and it is the same inductor current which has split into it. Therefore, the diode also has to have the same peak current value I naught plus delta I by 2, and the average value would be, that is also I naught 1 minus D. So this way you get the value of the current that will flow through the input and the value of the current that flows through the diode too. Now these are the critical waveforms that you have to be clear about, and when you do the simulation you should actually try to observe these effects in the simulation and see that this is what you are getting at. This waveform is the waveform of the capacitor current which flows through the capacitor. This would actually be the zero line. In the case of the inductor current, this line would be the I naught line. Now let us consider the current flowing through the capacitor, assuming that this green line is 0, there is no average. I naught component has flown to the load side. Now what is important in the capacitor is that for charge balance or amp second balance, this area should be equal to this area. So the amount of charge put into the capacitor should be equal to the amount of charge taken out. So this will be delta Q. Now looking at the capacitor waveforms, we know that this is the time the inductor current has magnetically charged up. So this is dTs, and this is the time when the inductor current is falling with a slope of minus V0 by L, and therefore this has to be the 1 minus dTs period. However, if you consider the triangle, this upper triangle and the bottom inverted triangle are similar triangles, because you see that the total height is delta IL. Therefore, the height of this triangle is delta IL by 2. The height of this part of the triangle is also delta IL by 2, and therefore the bases are also equal because they are similar triangles. The height is the same, and you can easily say that the base is Ts by 2. So going from minus delta IL by 2 to plus delta IL by 2, and this is a straight line. The midpoint, which is at 0 in the case of the capacitor, will be half the distance. Likewise, coming down, the midpoint will be half the distance in time, and therefore this will be Ts by 2. The other base will also be Ts by 2. So now let us look at this triangle. The area of the triangle will give you the charge. So the charge will be half base into height of the triangle, which is half. The base is Ts by 2 into height of the triangle delta IL by 2, which is Ts delta IL by 8, or further delta IL by 8 times Fs, which is the switching frequency. Ts is the switching period, Fs is the switching frequency. Now delta Q, or the change in the charge in the capacitor, is given by C delta V by the physics of the operation of the capacitor. Now this we know is delta IL by 8Fs, and therefore we can find out C. C is equal to delta IL by 8Fs delta V. Now this is a important relationship which you can use for finding the value of the capacitance that you need to put for the buck converter. Now out of these things, Fs is a design spec which is known. Delta V, what is supposed to be the ripple across the capacitance, is also obtained as an output ripple spec, that the capacitor is also a design spec, that the capacitor should not have a ripple beyond this particular value. The value of delta IL is also a design spec while designing the inductor. We will see that the delta IL value is assumed as around 10% of I naught max. So this is a starting design value which people use, or in some of the specification, minimum value of I naught is specified. So based on the minimum value of I naught, delta IL value can be obtained. So let us look at the inductor, finding the value of the inductor also, when where the value of delta I, finding the value of delta IL becomes clear. So for now you can see that the capacitor value can be calculated knowing the value of delta IL, delta V and Fs. Fs is known, delta V coming from design spec, delta IL also coming from design spec. So let us now look at finding the value of the inductor L. So we know that in the case of the inductor current, it is rising at the rate of V in minus V naught by L at that rate, and then it is falling at the rate of minus V naught by L. This is so for the case of the buck converter, where the average value of the inductor current is I naught. So this we have seen just now, just before this, the various waveforms, when we were studying the various waveforms. The inductor current goes by the Faraday's law. VL, the voltage across the inductor, is equal to L DIL by dt, and VL by L is the rate. So this is what we have here. Now you could use either of the slope. There is one variable in the, only single variable in the output, in the falling slope, so therefore we could use that. So let us say that this rate, I will just take the rate, absolute value of the rate. This slope finally is the delta dIL by dt, and because they are all linear straight lines, we could say delta IL by delta t. Now in this particular buck converter waveform case, delta IL is this much. So there is a change in delta IL from here to here in terms of time within this time. So this time was 1 minus d Ts for the buck converter case. You could do the same in the upward slope also, and you will get the same result. So delta IL is delta IL itself. So this is nothing but delta IL by 1 minus d Ts. So in this time period, we have this rate V naught by L. So writing here, you will see that V naught by L will be delta IL by 1 minus d Ts, or L equals, rearranging this equation, you will see V naught 1 minus d by delta IL Fs. So I will replace it by Fs because Fs is another design spec which is normally given. D is the duty cycle. So to get the maximum value of L, we could use the minimum value of D, that is D min. So if you consider L max, we would get V naught 1 minus D min, minimum value of D by delta IL Fs. Now how to get the value of D min? Now we know how to get the value of V naught. V naught is equal to V in into D. Now this V in is given and V naught is given. Normally V naught is a spec, V in is also an input spec. So D is actually calculatable. So we calculate D, which is equal to V naught by V in. And normally you will see that V naught is supposed to be regulated. It is supposed to be a constant value. It should be regulated in the face of variation in V in. So you will see that D could be V naught by V in max or V naught by V in min, and any value in between. So these would be the limiting values, where V naught by V in max will be D min value and V naught by V in value will be the D max value. So this is how we calculate. V in max and V in min are found from the input tolerance spec. So you can find D min and D max and then use this D min value here to find out the value of L. So if it works for the minimum duty cycle, it will also work for any other duty cycles. The value of L will be large enough to take care of any other duty cycles. Now one other issue is, here I mentioned that V naught is a spec, F is also a spec, Fs is also a spec, and V naught is also known, D is known. So everything can be used for calculating this except IL, and as a starting value you use 10% of I naught max load current. Use this and find the value of L. There is also another way. Sometimes the following spec is also given. Sometimes you will see that, let me write down this equation. L is equal to V naught 1 minus E delta IL into Fs. So you see that in the case of the inductor, this T, see the inductor current going up and down in this fashion. And here you have I naught. This is I naught. Okay. Now what would happen when R naught value is increased? If R naught value, the load resistance value is increased, you will see I naught decreasing. So I naught will keep decreasing, but you see that the delta IL and the rate, the slopes here will not change. They will, because they are determined by V minus V naught by L and V naught by L here, and therefore they are independent of the load resistor value or the load current value. So the shape of this triangular ripple will still remain, and the height of the ripple also will remain. So in the limit you will see that it may just touch, I'm sorry, the lines are not straight, so it may just touch the zero line like this. So this would be considered as I naught min, minimum value of I naught. That value of I naught where the inductor current ripple just touches the zero line would be the I naught min, because the average of that will be I naught min. So in this case, in this limiting case, if this was supposed to be the delta IL, so you will see that delta IL by 2, delta IL by 2 would be equal to I naught minimum. Or delta IL is equal to 2 times I naught minimum. And this is a very important condition that you can use for choosing the value of delta IL. Delta IL should be 2 times I naught minimum, where I naught minimum is specified. So this is specified. If this is specified by the user, then you can use this to find out the value of delta. If this is not specified, then you use delta L is 10% of I naught. This is how you would try to. Now here one more point is that this at I naught minimum, this is just touching the zero line. So this is at the boundary of continuous conduction. Boundary of continuous conduction. What it means is, if you go any further, we would have the triangle coming like this, and I am putting this in dotted. If there is a bidirectional switch, you will see the inductor current going negative, but the switch, if it blocks, then you will see that the inductor current goes like that. So this is a sudden change in the slope during this point. So the inductor current reaches 0, there is a change in the slope, and then again change in the slope. So that is why we say it is discontinuous, or the conduction period itself is discontinuous. You have a period where the inductor current is present, period where the inductor current is 0, not present, again it is present. So this is discontinuous conduction zone, or DCM we call this one. This type of an inductor current waveform is called DCM. And all waveforms above the 0 line, this type of waveform shown in blue, or continuous conduction, or CCM. So you should ensure that the inductor current is operating in CCM and not in DCM, because all the analysis that we have been talking about is for a continuous conduction mode.